Well, good evening, ladies and gentlemen, and welcome to the third annual USQ Festival of Astronomy. And you're very welcome indeed. It's great to see so many people here and so many young people who clearly develop a fascination with the planets very early on. In fact, I heard the story this morning about one of our staff members whose 2-year-old knows all the planets in our solar system, the heaviest, the lightest, the warmest, the coldest, and the moons of Jupiter. So the fascination can obviously start very young, and with many people, it lasts a whole lifetime. So my name is Professor Peter Terry. I'm the Director of Research, Training and Development here at USQ, and I run a program that helps to fund these sorts of events. So we're very privileged today to have our guest speakers come from interstate and internationally. And for those of you who may not know, to date, we have discovered, not me personally, but Earthlings have discovered 3,777 planets beyond our own solar system, the exoplanets. And people in this room have been associated with the discovery of more than 2/3 of those planets. So we have planet hunters aplenty in this room. And so you're hearing it from the people who really know what they're talking about. And with the launch of the TESS mission, which we're involved with, we're hoping that that number will go up perhaps by another 10,000, even 15,000. And USQ will be at the heart of that. Our observatory out at Mount Kent is, even as we speak, being equipped with more telescopes related to NASA missions and the European Space Agency, so that we will play a very direct role in the discovery of new planets, which is pretty amazing when you consider a little place called Toowoomba. So I hope you are excited about what you're going to hear this evening. And there's a couple of housekeeping things I have to do. In the event of an emergency, please exit the doors out there and hang around outside. Toilets are out there. Please switch your phones off. Other than that, pay attention. Now, I would like to acknowledge the traditional owners. Here at USQ, we acknowledge and honour the Jayabul and Jarowa peoples of the Toowoomba area as the traditional owners and custodians of the lands and waterways where USQ is located. Further, we acknowledge the cultural diversity of the Aboriginal and Torres Strait Islander peoples and pay respects to elders past, present and future. We celebrate the continuous living cultures of First Australians and acknowledge the important contribution that Aboriginal and Torres Strait Islander peoples have in Australian society. The University respects and acknowledges our own Aboriginal and Torres Strait Islander students, staff, elders, and visitors who come from many nations across Australia. And that's a particularly important acknowledgement today, considering the topic for our first speaker, who is Dr. Duane Hamacher. Dr. Duane Hamacher is an astronomer and senior research fellow at the Monash Indigenous Studies Centre in Melbourne, and an adjunct fellow of USQ's Astrophysics Group, which sits within the School of Agricultural, Computational and Environmental Sciences. After completing his Master's in Astrophysics, Dr. Hamacher completed a PhD in Indigenous Studies, studying Aboriginal astronomy, and is here today to present his talk, which is entitled Reading the Stars, 65,000 Years of Aboriginal Astronomy. I'd like to thank and welcome Dr. Hamacher to the stage.
Thanks, Professor. Thank you for that. Is this working? Excellent. So I would like to thank the university, the Center for Astrophysics now, and of course, Carolyn Brown, who's made all of this possible. It's fantastic to be able to come up to Toowoomba to speak to everybody about something that it's a topic of great importance and passion for me for the last 10 years. I'd like to start off by paying my respect to the traditional owners of this land and to any Aboriginal and Torres Strait Islander elders and people who would be in the audience today. You might notice from the accent, it seemed a little odd, this guy with the funny accent coming and talking about Aboriginal astronomy. But I grew up in the state of Missouri in the US, studied physics as an undergraduate. I was one of those really nerdy kids that grew into a really nerdy adult. I loved astronomy ever since I was about her size. And it's always been a passion of mine. But I've always been interested as well in the cultural aspect, in history, and archaeology, and geography. There were two passions I've always grown up with, but I had no idea how or if I was going to be able to put those together. When I studied physics as an undergraduate, I decided to explore. I took a whole bunch of units in archaeology and anthropology. It's something that I found really interesting, particularly at the crossroads of astronomy and culture. I came to Australia in 2006 to study exoplanets at the University of New South Wales. I came as pretty obnoxious, loud, annoying American, how we tend to be. And Dr. Christiansen was finishing her PhD at the time, and she had amazing resilience putting up with me during that time period, and taught me quite a bit about what I know about exoplanets. So even though I was doing a research project in exoplanets, I became increasingly interested in the crossroads of astronomy and culture. And I decided to leave astrophysics. I did a master's degree and immerse myself in that area. I didn't know what culture I was going to study at the time, but I thought, well, wait a minute. I love Australia. It's an amazing place. Cultures have been here at that time, 50, 60,000 years. Why not pursue this as an interest, as an academic career? So I went and studied Indigenous studies, which I can tell you was one of the most incredible challenges of my life. Coming from a physics background, being a non-Indigenous person, and being a non-Australian, coming into that space was something that is a steep, steep learning curve. But what I want to share with you tonight is some of the information that I've learned from the elders, from working with communities across Australia, Aboriginal communities, and predominantly communities in the Torres Strait. Now let's see if this is going to work for us. Oh, there we go. Because my background is in the sciences, I'm quite interested in the ways in which Aboriginal and Torres Strait Islander people have developed scientific knowledge over time, how they've passed that down through the traditions, and how they've encoded that in song, in dance, in narrative. So what I'm going to talk to you about tonight, the title, 65,000 years of science in particular, is how Aboriginal people and Torres Strait Islander people have incorporated this incredible depth of knowledge that's been handed down for thousands of years. So everybody, raise your hand if you've seen this map before. I hopefully can see everybody's hands. Excellent. This is just to give you an idea about the diversity of Aboriginal cultures here in Australia. There are several hundred, 300, 400 distinct Aboriginal nations, each with a unique language and culture. That means they also have a unique astronomy, unique astronomical traditions and knowledges. And something that's quite different from many people outside of those types of communities, we tend to hark back to the Greek versions of the stars, where the stars have one meaning. They're Orion, they're Cassiopeia, they're the Great Bear, they're whatever they happen to be. But among the Aboriginal and Islander cultures of Australia, they can have multiple meanings. And one of the things that I want to examine and discuss with you tonight are not just the knowledge, but how it's encoded in tradition. Now, the way we teach astrophysics now, the way we pass on knowledge in Western society, is mostly through the written word. It's through books. But we as humans have evolved not to remember long lists of dry facts, or to even have a structured written language. In the grand scheme of things, only a short period of time have we had written language. But instead, we learn through memory, and we learn through narrative. We learn through story. We encode scientific knowledge about the world around us, into stories, repeat that in songs, through dance, and even through different kinds of art forms. That's how we remember. We're hardwired for that. So as I go through tonight and explain some of the scientific knowledge, we're going to see how it's encoded in oral tradition, in song, dance, and craftsmanship. So before I start, what do I mean when I say science? It's important to acknowledge that there is a difference between Western science and Indigenous science. They're both ways of knowing the world around us, trying to understand the formation, the evolution, the process of the world around us, and the future. It's got some kind of predictive purpose. So what we'll talk about tonight are many examples of how astronomical knowledge is used to predict animal behavior, weather and seasons, to navigate across the country. These are all going to be different topics that we discuss tonight. But that's what I mean when I say science, understanding the world around us. Now, when we think of constellations, what comes to mind? Everybody yell out a couple constellation names. Orion, Big Dipper, Southern Cross. Excellent. When we think of constellations, we think of bright stars, we connect the dots, and it makes a familiar pattern. You do find those in Aboriginal cultures, especially Torres Strait Islander cultures, where I do most of my field work. But generally, in Aboriginal traditions, it's individual stars that represent characters in a narrative. But you find something quite unique in Australia. You also find it in South America. And that's the concept of dark constellations. Now, I know some of the astronomers who know me know what I'm talking about. Does anybody in the audience want to guess, what is a dark constellation? Do you know right up here? Exactly. It's the space between the stars, not the stars themselves. So from the southern hemisphere, you get a beautiful view of the sky. You can see the Magellanic Clouds. You can see the Milky Way. And all along the Milky Way, when you have dark skies outside of light pollution, you see these dark bands that go all through it, dark patches. They look like rivers, which many Aboriginal communities see them as. But these dark spaces trace out a whole load of different animals, serpents, crocodiles, all kinds of things. What I want to do is talk to you about one of the most common examples from across Australia. With Wiradjuri people, it's called Dinawan. We'll go ahead and play a short little 2-minute video for you guys. Hear it directly from the horse's mouth, so to speak.
I'd just like to talk about some traditional knowledge that was handed down to most of us Indigenous fellows in this area, and it's the emu in the sky. Around April, May every year, the emu will appear in the Milky Way. Just underneath the Southern Cross, you'll see a dark spot, a rounded dark spot. That's the head of the emu. In front of him, of course, is his beak. And as we follow it down, you can see his neck in the dark spots of the Milky Way. Comes right down to his body. You can see his legs. And you can see a couple of eggs underneath. At that certain time of year, it's the time for us to go out and collect emu eggs. We go out, of course, into the bush, always leaving some eggs for next year and for the generations to keep going. They only last up until early June. Anytime after early June, they start getting chicks in them. But before that, from April, May, you're pretty right to go gather.
So what we see here is a fantastic example that you find all across the country. Each of the different nations across the country have a slightly different view of the emu, maybe have a different story about how the emu interacts, the overall narrative. But the base level of knowledge is pretty much the same across Australia. It tells you about the behavior of the emu and about the changing seasons. But of course, what Ben Flick was talking about here is only the bottom level of knowledge. And we have to remember that in Aboriginal cultures and in Torres Strait cultures, there are multiple levels of knowledge. And the higher and higher the level of knowledge you go, the fewer and fewer people know that. So most of the stuff I'm talking to you about tonight really is the lower level. It's kind of the kindergarten, preschool version of it. Now I'm going to quiz you a little bit, so I want to see who's paying attention, and hopefully I haven't put anybody to sleep already yet. What was the gender of the emu? Did he say his or her? It's sitting in the sky, sitting on the eggs. Right? Raise your hand if you say his. Raise your hand if you say her. Okay, everybody that said her, you're wrong. Sorry. Said him. Why him? That's right. It's the males that sit on the eggs and incubate them. So what I want to talk to you about now is another level of this knowledge. So you can see the beautiful emu in the sky. When it rises in March or April, that signifies the breeding season. That's the time to go out and collect the eggs. And of course, by June time, you start getting chicks in the eggs. It's not the right time. But there's more to that. So this knowledge comes from Uncle Gillar Michael Anderson. He's a senior Uwalyi lawman from northern New South Wales in Gaduga. And the information that he provides, a story from his people, is more detailed. So we were fortunate that he'd shared multiple levels of that knowledge. Not very high, just coming up under the couple levels. Now we're sort of into, primary school. But we look up here, and what's interesting about the emu in the sky, it actually changes shape and how the people conceptualize it, even though the stars aren't moving. The whole thing is shifting across the sky, but the stars aren't moving to each other. But where it is in the sky has a different meaning throughout the year. You look at panel A in the top left corner up here, it's a female. She's running. Why is the female emu running? You might want to hazard a guess? Yeah? Not exactly. It's the breeding season. She's chasing after the male, that's right. She chases the male. The birds and the bees happen. She lays a clutch of eggs, then she takes off. It is now his responsibility to sit on the eggs and incubate them. So during that 2 or 3 month period, when the emu just rises after sunset, that's when that happens. Now a little bit later on, right about now, sort of, June, July, August, mostly June, July, the emu is a bit higher in the sky. Now it's seen as a male. He's sitting on the nest. He's incubating the eggs. It's his job to take care of the eggs, to protect the nest. A little bit later on in the year, back down here in this left corner, when the Milky Way at sunset, we're talking about sunset. So just after sunset, when it comes out, you see the Milky Way pretty much perpendicular to the horizon. This is when the male emu is getting up off the nest. Why is he getting up off the nest? The eggs are hatching. The incubation period is about 60 days, 58 to 60 days. So 2 months later, the eggs start hatching. Interestingly enough, during this time is when a lot of the male initiation ceremonies were held. I'm not going to go into any detail about them, of course, because most of that is secret. But that is the time of the year that ceremonies were being held. I'll talk about why in just a second. A little bit later on, the Milky Way just keeps swinging around, and now it's down low. But even though it would normally swing around so the head would be down here and the body here, the people say, well, when it's really low, it looks more like the emu is sitting in a water hole. It's sitting on the horizon. So it's kind of flipped around. And this is when you see the emus in the water holes. And as the emu sits in the water hole, it displaces the water, sort of like a version of Archimedes. The water comes out of the water hole and rains down as seasonal rain. And then it flips back under the sky again, comes back out a couple months later. So what you can see from this, the knowledge, the science encoded in here, tells you about the rising and setting position of the stars at sunset, informing you about seasonal change, informing you about behavior of the birds, and informing you about food economics. So when to go and collect the eggs for food. And of course, it links to ceremony. Because like I said, if you go back to this slide, right at this time of the year when the Milky Way is perpendicular to the horizon, that's when you'd see the boar in the sky. Now, one thing that the elders have taught me is everything on the land is reflected in the sky. The sky is a law book. It's a textbook. It's a science book. So these boar grounds on the sky are reflected in the Milky Way, and they actually line up to the Milky Way in August and September when those ceremonies are being held. So it's seen as a pathway, a direct connection between the land and the sky. So all these traditions have a scientific component, and they have a cultural and social component. So moving on a little bit, star maps. Everybody's heard about celestial navigation before, right? The Polynesians are some of the most famous about it. For having it, you follow a star, you know where the star sets on the horizon, you know its angle on the horizon, which is called the azimuth. And if you know that, you can determine how to find your way across land or sea. Now, for many, many years, anthropologists said that Aboriginal people didn't navigate by the stars. I've got elders telling me they do, but that was a common thing that was what we do find is that, yes, Aboriginal people navigate by the stars, but there's also a very different way by which Aboriginal people navigate, and that's by the use of star maps. Star maps is not following a star at night in that direction to get where you're going. It's memorizing how to get from one point to another, long distances, maybe from Gaduga to the Bunya Mountains or to Carnarvon Gorge for trade and ceremony. You figure out how to get there, the best route. You know the landscape, you know where the water holes are, you know where the food is. Once you figure that out, you have to remember it. So you develop a star map. You find stars in the sky that roughly equate to those positions. You create songs and stories that describe it. You teach the younger generation these stories when those stars are up in the sky. And then a bit later on in the year, when it's time to travel, you don't travel at night, you travel during the day. But you're not following the stars, you're following the mental map that the stars helped you remember. And what's really interesting, here's Uncle Gillar again, telling us these are some of the different stars that would be followed to go to the Bunya Mountains, to go to Carnarvon Gorge, starting down in Gaduga. Now, when you think about this, you can overlay the star map on a map of Australia, and you find something quite remarkable. Well, the Aboriginal people would have trade routes, walking routes. They'd know where to stop and camp, where the food and water was. So when the colonists first came through, the Aboriginal people, being very open and friendly, not realizing what was going to happen later on, of course, took the people, the colonizing people, through the landscape. Those pathways became roads and later became highways. And the areas we would stop for water and food became settlements and later on towns. So now if you superimpose that, you find that our modern highway network is based on Aboriginal star maps. And that many of those towns we see in southeast Queensland, the very northern tip of New South Wales, are actually represented in Aboriginal star maps by individual stars that you can identify in the night sky. It's a really novel and different way of thinking about celestial navigation, not by following stars, but by having a mental map. Now, of the many different uses you have for astronomy, when the stars rise and set, looking at positions of stars, you can also look at the properties of stars and how they change. The elders call this reading the stars. This is what I've been taught. They say you have to know how to read the stars. And what they mean by reading the stars is knowing how to observe and interpret even the most subtle ways the stars change properties. So what do I mean by star properties? When you look at the stars, what do you notice about them? What's one of the properties of stars in the sky? Their brightness, right? What else? Their color. Excellent. And what do you notice about the stars when you look up at night? We have lullabies and story and poetry about that. They twinkle, right? So if we know, as it turns out, something I didn't know through all my years of training and studying in physics and astronomy, I never knew that you could tell something very important by simply observing how the stars twinkle. And I'm going to talk about that in a minute, but what I want to do now is I'm going to bring up the video, and I'm going to translate the video. So before we play it, this is Uncle Allo Tapham. He's a senior elder on Murray Island in the Torres Strait. If you're not sure what that is, this is the home of Eddie Kweki Mabo. So Uncle Allo was telling me all about how you read the twinkling of stars, and the other elders told me about it. And when I was asking him some more detail, he says, we have a song about this. I said, you do? He's like, yeah, we played it for you the other day. Of course, they were singing it in Miriam Mir, which is the traditional language, which I didn't know. But he played the song for me and allowed me to record it and to show everybody else. So what I'm going to do now is I'm going to play the video, and I'm going to translate as he's singing the song. Why is it so calm tonight? Why are the stars twinkling so brightly? Like embers in a fire. It's a sign about the changing big wind. That takes rain clouds in the south, sweeps them from the northwest. Why are the stars twinkling so brightly tonight? Stop there. So when he's singing the song for me and explaining to me how you read the twinkling of stars, it was something I found fascinating because I had never thought about it. It never occurred to me that you could actually predict weather and seasonal change by knowing how to read them. So this story in particular talks about later in the year, October, November, December. It's the drier, cooler season, the Sager, but there's also a special season in there, something they refer to as the doldrum, which is a navigational term meaning still. And he says, during this time of the year, the weather is beautiful. It's very hot, but there's no clouds, not a breath of air. It's just dead still. When you look at the stars at night, you look at the stars that are high above, not the ones low on the horizon, but the ones high above. Are they twinkling? They're twinkling very rapidly, even though it's calm on the ground. The farmer knows to begin planting his crops, banana, sugarcane, because the wet season is coming. And you're going to see it's the trade winds shifting from the cool southeasterlies to the hot northwesterlies. The hot northwesterlies bring the monsoon rains. So as many of us know, as everybody should know, twinkling of stars is caused by turbulence in the atmosphere, or pockets of air moving, causing the refractive index to change. But also, other factors can change what we call seeing conditions in astronomy. The colors of the stars can change, not just their brightness. Do they become fuzzy, they sort of lose their resolution a bit. They become sort of blurry. If you know how to read that, it can tell you about weather. Now, one of the elders, a different elder, sat down and said, you look at the stars that are high above, you can tell how fast the wind's moving by how fast they twinkle. And if they're twinkling quickly, they're kind of blurry, and they look very blue, it's going to rain imminently. And that was one thing that really stood out for me, because I thought, well, okay, what makes them blue? As astronomers, we know that when you go out at night and you adapt to your night vision, blue is not a color you really see very well at all. The blue light gets scattered in the atmosphere. It's why the sky is blue. We're not going to see it very well. But if a lot of humidity is in the atmosphere, that water vapor in the atmosphere makes the stars a bit blurry. It also absorbs all the red and green wavelengths of light. So it's most of the blue light coming through. So the elder's explaining the basic physics of twinkling stars and how it's used, but they're not saying it in physics terms. But that's where you have this crossover between culture and science. That's where you have this crossover, knowing how to read the stars just by looking at the subtle ways in which they twinkle. I thought I'd put a little sciencey graph up so everybody can see that. This is simply the wavelength of light. So you can see the bluer light down here going up to the redder light at this end. And this basically tells you how much water absorbs that light. So you can see up here, it absorbs a lot. But down here, it doesn't hardly absorb anything. So this is why the stars appear kind of bluish if there's a lot of humidity in the atmosphere. Also, you can predict weather by looking at moon halos. So moon halos are caused by ice in the upper atmosphere that refract light in a certain way with these hexagonal crystals. I believe they're hexagonal. You get these big 22-degree halos. Sometimes you get 44-degree halos. But who's seen a halo around the moon before? Most everybody has, right? Sometimes they're pretty clear inside. Sometimes they're like this. They're very fuzzy. In many Aboriginal cultures, just like the Torres Strait, it's seen as a man in the moon building a hut to keep himself dry, because moon halos predict wet weather's coming. With the Gaboroi and Uwalyi people, as Uncle Gillar explained to us, and we found in the old records from the 1800s, the people saw the same thing. But they say, look inside the moon, between the moon and the halo. If it's really clear and you can count several stars inside, it'll be several days before it rains, if at all. But if it's really fuzzy, you can't see any stars inside, rain is imminent. It's going to happen very, very soon. Well, what causes the ice crystals in the upper atmosphere? Low fronts. What do low fronts bring? They bring rain. If there's a lot of humidity in the atmosphere, it's going to look like this. It's going to be really fuzzy for the same reason I talked about the twinkling stars. But if it's very clear, that means the air is pretty dry and it might not rain. So just knowing how to look at moon halos and twinkling stars can help you predict weather and seasonal change. Now, something else is quite interesting about the dynamics of the sun and the moon. Now, for those of you who haven't been on campus very much, is it the Gumby Gardens just nearby? There's a beautiful little stone arrangement that was put there to recognize that Aboriginal people have been observing the solstices and the equinoxes for millennia. And there are stone arrangements across Australia that pinpoint this out. This is a very sort of simplified version of that. But you sit on the flat stone, and there's 3 stones out further away. One marks the winter solstice, one marks the equinox, and one marks the summer solstice. So Aboriginal people very well aware of the different phases of the moon, the different dynamics of the sun, the different positions. When we look at the phases of the moon, it's still weird for me. Even after 12 years, I keep thinking the moon's upside down because I'm used to the northern hemisphere view of that. But many of the Aboriginal traditions talk about the moon being a man. In fact, most of them, not all, but most say the moon is a man and the sun is a woman. They're usually spouses. There are lots of different stories that talk about the phases of the moon, but they very commonly link with tides. So in some countries up north, Yolngu people in Arnhem Land talk about the moon being a man named Galindi. Galindi had several wives and daughters. And he was pretty lazy. He didn't like to do much. So he just sort of sat around and made them do all the activities, collect the food, do everything while he just sat around and ate. What happens when you just sit around and eat and don't do very much? You get bigger and bigger and bigger. And eventually, you reach your peak. And at that point, what tends to happen is your spouse says, no, we're done. That's enough. His daughters and his wives got very angry with him and decided to exact their revenge by starving him and then chopping bits of him off with their axes, as one does, right? So he begins to wane away until he dies for 3 days before coming back to life. And what you find all around the world and all across Australia is the idea of the moon dying for 3 days before coming back. That's the period of the new moon. It's very close to the sun in the sky, but it dies, it wanes away, and then it comes back to life. Something happens once in a great while. And there's a Gamilaroi story that I find is very interesting. This one talks about how it's same. The sun is a woman, the moon's a man. The sun is a woman. She falls in love with the moon man, Balu. Balu he doesn't feel that way. He doesn't reciprocate. He just wants to be friends, right? So he says no thank you, but she doesn't take no for an answer. She wants him. So she chases him around the sky. He tries to avoid her advances by zigzagging around the sky. So if you see the path of the sun, called the ecliptic, sometimes the moon will be on this side, sometimes it will be on that side. And it kind of goes back and forth. He's literally dodging, trying to get out of the way as she's coming for him. Sometimes he gets away, his confidence builds up, he's a full moon, she starts to get close to him again, and he gets very scared. But he manages to get away with no problem. But once in a while, once every few hundred years, she gets a hold of him and attempts to consummate the relationship. He calls in the spirits that hold up the sky to tell them to collapse the sky if she doesn't get away. So a few minutes later, she lets go and goes back to the dynamic again. So what we see here are the Aboriginal traditions talking about the sun and the moon being superimposed, which is exactly what we see with the solar eclipse. And we find examples of solar eclipses, despite them only occurring every few hundred years from any given location, all around Australia from many different Aboriginal groups. Now, I was talking before about the solstices and the equinoxes. I'm trying to keep track of time. If you were to watch the sun, photograph the sun every night at the same time, around sunset or sunrise, it makes this very peculiar figure 8 infinity kind of shape. And what we see here from the southern hemisphere, this is when it reaches its southernmost azimuth. That's the summer solstice. Its northernmost azimuth up here. And exactly halfway in between are the equinoxes. Now, you might think, well, isn't the equinox where they cross over? It is not. The reason it crosses over is because the moon doesn't orbit the Earth in a perfect circle. It's slightly ovate. So sometimes it's a little bit closer to us and it moves faster, and then as it goes further away at apogee, it becomes slower. So faster here and slower here, but exactly halfway between is the equinox. That's what these stones out in the Gumby Gumby Gardens show. And that's what stone arrangements around the country show. But as I found out, I was taught just a few months ago when I was in the Torres Strait, I went to Moa Island, to the village of Kuban. David Bozen is an elder there and an artist. And he told me that his father was what the Torres Strait Islanders have as an astronomer, Zugabul Mabaig. Zugabul Mabaig means star man. That is their job. They are professional astronomers. They're the ones that watch the sky, they watch the stars, they watch the moon and the sun. They tell the people when to hunt, when to plant gardens, when to hold ceremony, when the seasons are going to change. That was their job. Professional astronomer, Zugabul Mabaig. If you're in the village of Kuban, which is right here in this little peninsula, and you look out, you see these big, beautiful islands populating the background, this archipelago of islands. And when I went out there, it was an amazing sight. They tell me, if you watch where the sun sets relative to those islands, it can tell you the solstices, it can tell you the equinoxes, but not just those extreme points in the middle point. If the sun sets over a particular island, that means the wet season's coming. As it moves down a little bit further, that means it's the dugong season. It gets down to its point and it comes back. That's a turtle breeding season. All the different seasonal change is encoded within that. So here's a simulation, and I didn't even think about putting a photograph because I've got photographs of the solstice I took when I was up there in June. But this gives you an idea. You can see dips in the horizon or where the islands meet the sea. These are the significant points. So Torres Strait Islander people have always known very well the setting positions and rising positions of the sun throughout the year and use that to determine a whole lot of different things. Now, the importance I give to that is that throughout a lot of the academic literature, there was never any evidence. People said, well, Aboriginal people, they didn't really know about the solstices. Hang on. We watch the subtlest changes in the stars, have traditions about eclipses, have traditions about aurora. You're going to tell me they didn't notice the sun setting 60 degrees across the horizon every day? Of course Aboriginal people knew about that, and still know about that, and still utilize that today. This is another thing. I'm probably going to have to finish with this one. We don't have too much more time. But this is something that's very interesting. This is only something that we've really learned about in the last year. And that's the variability of stars. Now, what do I mean by variability of stars? What is varying about the stars? This is something the whole astronomy group knows about because that's what they study. It's the changing brightness of the stars. Some stars have things, might have a planet moving in front of it, which is the technique that the whole group here uses. That makes the starlight dip just a little bit. But of course, you're not going to see that with your unaided eye. Sometimes you get a bright, like a supernova, a star explodes, becomes very bright in the sky for a while, then fades away again. But some of the stars, particularly the red ones, pulsate. And they'll get brighter and fainter over time, and you'll be able to see that with your naked eye. Now, back in the 1830s, William Herschel was observing stars from Cape Town in South Africa, and he kept a list of the stars, the brighter stars in the sky, in order of brightness. Up until that point, it had been dogma for almost 1,500 years that the stars were invariable and unchanging. That was something that Aristotle said, and that held. So he was thinking about, well, maybe this isn't right. And he discovered that one of the stars does vary. When he put that list of stars down, if they stay the same brightness, it'll always be the same rank. But one of them was moving around. And that's when he discovered the stellar variability of the star Betelgeuse. We have Aboriginal traditions that talk about variable stars. There's one Aboriginal tradition from Yolngu people, and I put this as a visual aid only. This is actually a man and a woman from Port Jackson, which is Sydney, but I couldn't find a better picture. The story talks about two brothers who were in a canoe out at sea fishing. They didn't notice a storm brewing. When they did, it was too late. They began pedaling back as fast as they could, but the storm capsized their canoe, and they had to start swimming. The younger brother, who was not as strong and less experienced, started to drown. So the elder brother, at the expense of his own life, saved his younger sibling. When he got to shore, the younger sibling got to shore, the people ran down to find out what happened, and he told them his older brother had saved his life. So the community held a ceremony that night to reward and recognize and honor the elder brother for his sacrifice. And a short time later, a very bright star appeared in the Milky Way. And they knew that was the elder brother. He faded away, and the younger brother grew up to be an old man. Before he died, he asked the ancestors to place him in the sky near his older brother so they could be together. They became the stars Shala and Lasath. Those are the Greek traditions. Those stars are in the stinger of Scorpius, which you can see outside tonight. Well, a bright star appearing in the sky and fading away in the middle of the Milky Way, it could be a supernova. We don't know for certain, but there is a fantastic candidate. In the year 393, a bright star appeared in the sky. The Chinese noted it as a new star, a nova, in the constellation of Hui, which is right in the stinger tail of Scorpius. So it's exactly the right part of the sky, right about here, is one of the brighter supernovae in the last couple of millennia. It certainly is interesting because these two stars right here are the brothers. So it's entirely plausible that Aboriginal people observed this supernova, and that's the narrative, that's the story they developed for that. But we do have some examples, some more solid examples of Aboriginal people observing variability of stars. This story, which will be the last one I talk about tonight, comes from the Ngarrindjeri people of South Australia. This is south of Adelaide along the Coorong, the mouth of the Murray River. Many of the different Ngarrindjeri clans and groups tell the story of Wyangari. Wyangari was a young man. He was an initiate, going through initiation. And during this time, he became what is called a Narambi. I hope I'm pronouncing that correctly. I'm not even sure. He became a Narambi. During this time, he had to go through a period of time of suffering. He wasn't allowed to wear any clothes. He was covered in red ochre. In fact, Wyangari means red man. He wasn't allowed to eat any food or have any contact with other people. And he was certainly not allowed to have contact with women in that way, wink, wink. One day he was walking along the riverbank, took a reed, bent down in the water to get a drink from the river. When he did that, some of the red ochre spilled into the water and went downstream. A little ways downstream were two women. They saw this red ochre and they became very curious, like, what's this? Where's it coming from? They went up and they saw him. He's a very young, very attractive man, all ochred up for ceremony, and they thought, we want to make him our husband. And I say that euphemistically for the younger audience. So they followed him to his hut that night. When he went to sleep in his hut, they morphed into emus, and they made the sound of emus to draw him out. When he heard the emu sound, he ran outside, and they morphed back into the beautiful women, and they went into their hut, and I'll let you connect the lines about what happened. Well, there's two problems with this. Number one, he broke sacred traditional law that forbade him from having that kind of relationship. The second thing is that those two women were the wives of his brother, Nepali. Now that may seem very strange, but in a lot of Aboriginal communities and Aboriginal cultures, when you reach a certain age, you lose contact with certain parts of the family. Certain members of the family become taboo. It's part of a very complex marriage and totem system. Well, somebody saw all of this happen. It was his mother. Yikes. She was furious about the infidelity of the wives and about her son doing what he wasn't supposed to be doing. So she told Nepali. Nepali, as you can imagine, was pretty upset about this, so he decided to exact his revenge by setting the hut on fire while the three were asleep. They woke up in time and managed to escape. Running downriver, they realized they faced death as punishment for what they did. So Wyangari cast a spear into the Milky Way, and he pulled himself and the two wives up, where he became a bright red star in the Milky Way. The two stars on either side of him of similar brightness are the two wives. He comes up in the sky very high every springtime. And then every once in a while, he gets hotter and brighter. And this signifies his passion and serves as a warning to the people to watch their carnal instincts and to not break sacred tradition and sacred law. But that passion dies down again for a while. It just kind of comes back and forth every once in a while. Well, what's interesting about that star is that a lot of the anthropologists in the early days didn't know what it was. They thought it must be Mars. It's red, it's in the sky, it's Mars. And they said, well, it sort of changes in brightness. That's because Mars sometimes close to us, like it is right now. You go outside, Mars is at opposite the sun in the sky from us. It's closest to us for the next 15 years, and it's really, really bright. They couldn't quite figure out who the wives were. What are they, stars? Are they other planets? This story got repeated throughout books in the literature for 150 years. Nobody really knew what they were. It wasn't until last year that a colleague of mine, an anthropologist, sent me a paper he wrote looking at all the different stories, all the different versions of that story, and said, look, I don't think Waiangari is Mars, but I'm not sure. You're an astronomer. Tell me what you think. And I read through it, and I said, well, there's only one very obvious candidate for these 19 different reasons. It is star Antares. And the wives are the stars Tau and Sigma Scorpii on either side of him. Now, what's kind of ironic about this is, what does the word Antares mean? Does anybody know? Got a few astronomy enthusiasts in the audience. It means like Ares. Who was Ares in Greek mythology? God of war, right? And what was the Roman god of war? Mars, right? Exactly. They're rivals in the sky. Sometimes Mars comes very close to Antares. They're both bright. They're both red. They're both fighting for dominance. So you can literally think of as Antares means not Mars. But what's also interesting about the star Antares is that it's variable, and not just by a subtle amount. I'm going to throw another graph up there. The astronomers are going, oh yeah, everybody else is going, what? This simply shows the brightness of the star over time. So if it stays the same brightness, it should be a straight line. But it's not a straight line. It's got some weird reactions. It does this whole pulsating thing back and forth, and not in a regular manner, but a semi-regular manner. And it varies by a full magnitude. It's the way we measure stars. It's something you guys can look up tonight when you go home. But it's definitely noticeable to the naked eye. But it only happens every 4 to 6 years that it'll have this major difference. So you have to be watching the stars very closely over a couple of years to be able to notice this change in brightness. That's something Aboriginal people did very well. This is not the only star in the night sky, the only red giant that was observed to be variable by Aboriginal people, but it's one example. And it's phenomenal when you think about this, because Western science says, no, it was William Herschel in the 1840s that discovered the variability. But what you have are Aboriginal traditions that were recorded in the 1840s that go back way before that. This totally challenges and changes the history of science and tells us astronomers that we need to be looking more closely at these ancient Aboriginal traditions. You've got 65,000 years of collective wisdom, of collected observations of the sky, and close connections to how that relates to everything on the ground. There's a lot we can learn. If we had looked at these traditions, we'd notice a bright object appearing in the Milky Way. Well, let's train our telescopes there and see if we can find a supernova remnant that falls within the last several thousand years. And if we did, we would have found evidence of the 393 supernova. If we'd have looked at these traditions, instead of thinking of them as myths and legends with no value, if we realized they're complex knowledge systems, we'd be able to recognize these traditions are talking about stars changing in brightness. Let's look. Do they? They do. We can learn. Modern astrophysics can learn from Aboriginal traditions if we just pay attention. So now that it's about 7 o'clock, I had a longer talk prepared, but I'm just going to zip through a few things to get to the end part. Oh, this is one thing, 2 things I want to mention quickly. Number 1, I'm part of the International Astronomical Union Working Group on Star Names. It's a long title. What we have done is gone through and officiated one name for all the bright stars in the sky. Now, you may have heard earlier this year about one of the stars in the Southern Cross getting an Aboriginal name. It's the 5th star we call Epsilon Crucis. So alpha, beta, gamma, delta, epsilon. We astronomers are creative, I know. It simply ranks the star by brightness. It's called the Bayer designation. What's important is now that star right there is known around the world officially as the name Guinan. That comes from the Wordaman people of the Northern Territory. And I thought it was pretty fantastic that the Southern Cross now has a globally recognized name. That star does, which I think a few individuals, perhaps that have tattoos for the wrong reasons, might find that a bit of a challenge. On that note, I'm heading to the IAU tonight. I fly out at 2 o'clock in the morning to go to Vienna for our big meeting, and we're about to officiate a few more Aboriginal star names. But there are also a whole lot of star names from the San people of Africa, Polynesia, Melanesia, a whole lot of different cultures around the world are also getting star names officiated. Last thing I just want to mention really fast is that how many people here have been to the Brisbane Planetarium in the last 4 months? The astronomer. A few people. All right. If you get to the Brisbane Planetarium, you're going to see a new exhibition. It is a permanent exhibition called Skylore, Aboriginal and Torres Strait Islander Astronomy. It's on the outer wall of the planetarium. It's 13 meters long, and it's 1.5 meters high, and took me 6 months to curate. What this is, it talks about 15 different examples of Aboriginal and Torres Strait Islander astronomy, mostly from 3 different communities. The Meriam Mir, where I work with in the Torres Strait, the Wordaman people, who, that's the star name, Guinan, and the Uwali Gamilaroi people, Uncle Gillar Michael Anderson. So a lot of the examples tonight, plus a few others, you'll see at the exhibit. In fact, right there is the star maps. I didn't talk about bays on the shark, but here's the twinkling stars. You'll see some examples of this over there. So that is now permanent. I'm hoping in the very near future to write a small book with one of the Aboriginal astrophysics students who's working with me. Her name is Crystal Dinopoli. She's at Monash. This is the next generation of Aboriginal astrophysics students. At the moment, I'm trying to work on some books with these individuals. Carly Noon, who's quite famous, you may have seen her with Brian Cox at Stargazing Live a couple of months ago. In Sydney, she had a giant picture of herself on the sides of buses, advertising Aboriginal students studying mathematics. So she's got a very amazing career. She's working on a master's degree in astrophysics at ANU. Crystal Dinopoli is working on her undergraduate degree in astrophysics at Monash, where I work. Kirsten Banks has now become an absolute superstar. She's on TV all the time, on the radio all the time, National Geographic, international documentaries. She's going to be the next major science communicator to come out of Australia. She always joked about how, not joke, she always said she wanted to be the next Brian Cox. And when Brian Cox was up here, he said, no, you're not going to be Australia's first Brian Cox. You're going to be Australia's first Kirsten Banks. So her career is taking off. And then Willie Stevens, a friend of mine, was working at Sydney Observatory as one of the tour guides. So several years ago, when I started, we didn't know of any Aboriginal people with PhDs or studying astrophysics. Now we have a whole generation who are coming up and carving out a space in this area. So if you want to learn more about this, all the examples and more I talked about tonight, go to aboriginalastronomy.com.au. We just launched this site a few months ago. It took a year to build, and it's absolutely filled with stuff. And you'll see it constantly being updated. Thank you.
Thank you very much, Duane. We do have time for a few questions. How are we going to run this one? Who's running with the microphones? Okay, so a bit difficult for me to see. So if you put your hand up and wave quite well, with particularly interesting questions from our younger members of the audience.
Any kids' questions?
Can't see any hands. Yeah.
I can bring the lights up a little bit. For those of you, before any questions come, I should note that just yesterday, Kirsten and I published an article in The Conversation about planets and planetary motions in Aboriginal astronomy. I didn't really talk about any of that tonight. So go on to The Conversation. It just came out yesterday. Have a look at that.
So, don't be shy. Any questions? There's one just here. So, and there's...
Hey there. Since no one's asking, I'd love to ask you a question about the planet that we see as Venus. I think the Indigenous name for Venus means morning star, which in Latin means Lucifer, which connects to, Greek. I'm not an astronomer, by the way. I'm an artist, so excuse my terminology. But what I'm really interested in is at certain times of the year is when there's a thread of stars that trails behind, and that's a way of Indigenous culture communicating with deceased.
Well, I think what you're talking about is Banambir. Banambir, it's slightly different names and different traditions about Banambir across Arnhem Land, but it's seen as the morning star. So Aboriginal people knew very well that the object that's the morning star and the object that's the evening star is the same thing. You never see it in the sky at the same time, but it does a transition. So what the Aboriginal people in Arnhem Land do is have a ceremony about Banambir, and they have to plan well ahead. They have a ceremony that starts in the evening and goes all night long, and just a couple of hours before sunrise, Banambir will rise in the sky between there's a little island called the Island of the Dead, and the mainland, and it will rise in that exact spot. And they see a rope that ties Venus to the sun. We could think of that as gravity, which is what it is, but they build these amazing Banambir poles that have white feathers. It's seen as a connection. It speaks between them. What we believe that is zodiacal dust. That's dust in the plane of the solar system that sunlight reflects off of. You need to have very dark skies to see that, but I've seen it myself in the Torres Strait many times. I'm sorry? Just real fine remnants of the formation of the solar system, just real fine dust, bits, chunks, gas that's in the plane of the solar system. So that is something very interesting because Venus rises and sets at different points along the horizon over a cycle. But if you count the days, you'll know when to hold that. And when Ray Norris, an astronomer, asked one of the elders how they knew when to hold the ceremony, they said, well, we count the days. What they were describing is a synodic period of Venus. And that is in the conversation article I just wrote. So you can go on that, see the article, and see the paper we published on it.
Thank you.
Hi. I've actually been reading bits and pieces of your stuff for a couple of months now for work. I'm working with a startup in St. Lucia that's made an astronomy app for people who are visually impaired and blind. We're trying to integrate the Aboriginal names since it is an Australian app, and that's how I came across your work. But other than yourself, what is the best resources for me to look for that?
URL I put up right there.
Yep.
Pretty much every paper that's been published on the topic, all the media, the articles, the books, the hardcore research, everything is on this website.
Excellent.
So if you don't find it on there,
yep,
doesn't mean it doesn't exist, but let me know, and I'll try to get it up. But you need to talk to, obviously you would talk to local elders and try to get that traditional knowledge. Australian Aboriginal astronomy is still in its infancy, even 10 years on, even, the years before that, people were doing research. It's growing really rapidly right now, but it's still a very small cohort. It's me and a few other people, that's it.
Question right there.
Hi, I was just wondering if things like light pollution have affected any tribes being able to pass down this information.
That's a very good question. And the answer, I believe, is yes. So we can think of these stories, these songs, these dances as intangible heritage. Tangible heritage being something you can touch, stone arrangements, a place, So this intangible heritage is under threat, and light pollution is one of the biggest threats to intangible heritage. How can we maintain a connection with the sky if we can't even bloody see it? The Southern Cross is a great example. All Australians, regardless of where you come from, have some connection to the Southern Cross. It's on the Australian flag. Aboriginal people have traditions going back millennia about the Southern Cross. In fact, We Don't Need a Map was a great film by Warwick Thornton, talks all about that. But the city lights and light pollution is so bad, you can't even see Gina, you're not going to be able to see that from the city. It's too faint. Even the fourth star of the Southern Cross is getting to that point. And the rate we're going, you're not going to be able to see any of the stars before too long. But we're losing our cultural heritage. We're losing our connection to that. And how can we maintain a sense of awe if we can't even see the stars? So light pollution is a major problem. There are solutions to that. There are also problems. So LED lighting which is amazing if you want to save energy, is really, really bad for light pollution because it emits a lot of light at the blue end of the spectrum, which scatters. And because it's so much cheaper, people use a lot more of it. So LED lighting is causing a really bad, or is having a really bad impact on light pollution. But there's amber LEDs. These are LEDs that work in the redder wavelengths that don't have that same problem. So some of the work that we're getting into now is with urban design and city planning. How can we reconnect people with the night sky when you live in a city? How can we find solutions to the light pollution problem, knowing that we can't tell people to turn the lights off and the population is going to be growing? How do we find solutions for that? So we're actually looking at Aboriginal astronomy and intangible heritage as ways of trying to find out how we can help. So yes, in more of the light polluted areas, people are losing their connection. And I'm sure that happens with Aboriginal cultures. But when I go to the Torres Strait, on Murray Island, the skies up there are breathtaking. Breathtaking.
Well, unfortunately, we're going to have to wrap it up there. It's been an absolutely fascinating talk. I've certainly learned a lot from it. And I'd just like to give Duane just a little gift from our own Queensland College of Wine Tourism in Stanthorpe, so locally produced.
Thank you very much. I do have to get on a plane tonight, and I've got carry-on only. So
I have to drink it straight away.
That could be.
I'll help. Anyway, please once again, just please thank Dr. Duane Hamacher. Okay, I'd like to introduce our next speaker. Now, it's Dr. Jesse Christiansen. She is a research scientist at NASA's Exoplanet Archive, based at the California Institute of Technology, and is one of the leading researchers working with NASA's successful Kepler Space Observatory. Dr. Christiansen is passionate about championing diversity and underrepresented minorities, particularly women, in STEM, in the science, technology, engineering, and mathematics area. She is actually a local girl originally, from just outside Ipswich. And today we look forward to listening to Dr. Christiansen's presentation, which is entitled On the Road to a Billion Planets. Thank you and welcome, Dr. Christiansen.
Hello, is it on? Do I need to do something? Everybody stand up. I'm not kidding. Everybody stand up. Hello. Hello, hello. Wiggle. We've all been sitting down for more than an hour. Wiggle. All right, stretch. All right, sit down. All right. Now we can get it. Now we can get back into it. All right. My name is Jesse Christiansen, and I have a pretty cool skirt. And that was my presentation. Thank you very much. All right. I'm going to take you on a journey today, not quite as long as Duane's journey, but I'm curious to talk to Duane more about that, of our discovery, of humankind's discovery of planets around other stars. And I've got post-it notes on the floor that I need to stay within. All right. But I can already hear you saying, wait, wait, wait. What do you mean planets around other stars? Let's do some background, homework. This is our solar system, not to scale. This is our sun. We have 1. These are our planets. We have 8. Boo, hiss, shh. I know, I'm sorry about Pluto. It's not my fault. Blame the International Astronomical Union. Send Duane and send an envoy. So we have 8 planets. We also have dwarf planets, which is the new bucket that Pluto got put into with all his new friends, Sedna, Makemake, Eris, Ceres, and many more. That was the problem. We kept finding all these things and we needed to decide what they were. We also have minor planets, which is basically everything else in the solar system that's bigger than about a grain of dust that we've managed to catalog. We have over 700,000 of those. It's actually pretty busy out there. But what are exoplanets? So for thousands of years, and maybe tens of thousands, I really want to talk to Duane, we've been thinking about this idea that there might be planets around other stars in the sky. So our sun is a star. It's a boring, middle-aged G star. It's a yellow star. The sky is full of them. If our star has planets around it, why wouldn't the other stars have planets around them? So the ancient Greeks were talking about this, but they were talking about it in a very hypothetical way, kind of the way we talk about multiverses today, just this kind of really crazy out there idea that's impossible to test, but kind of fun to talk about. So that's the way they were talking about it. Let's fast forward a very, very, very long way and come up to 1592, the Renaissance. Great time to be a scientist, unless you said something stupid about the church, which this man did. Giordano Bruno. He was an Italian mathematician who Australians might call an ideas man. His whole thing was to sit around and think of cool ideas and say stupid things about the church. But this is what he said about exoplanets. I'll just read the quote for you. There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets. This was before they knew about Neptune and then Pluto and then not Pluto again. We see only the suns because they are the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse and no less than inhabited than our Earth. So he's introduced 2 really big ideas here. One is the problem. It's really hard to find planets around other stars. Planets are small, stars are big. Planets are faint, stars are bright. So he's hit on the problem. We understand why we can't see them. He's also brought up the idea that there might be life out there, that those planets might have life on them. It's very exciting, a very dangerous idea for the Renaissance. And he was actually subsequently burned at the stake about 8 years later for, amongst other things, claiming the plurality of worlds. All right, so let's fast forward again to 2010. So for thousands of years, we've thought about the idea that there might be planets around other stars, and we've identified what the problem is. Finally, in the 90s, technology caught up with our imaginations, and we were finally able to detect exoplanets around other stars. So I want to tell you about the first kind of planet that we found. I think I only have 2 plots in this talk, so stick with me. We can do it. On the horizontal axis here, I'm showing the orbital period of the planet. So that's how long it takes to go around its star. How long does Earth take to go around the star? 365 days. All right. So these magenta squares here are actually the inner solar system planets. Mercury, Venus, Earth, and Mars. So that's Earth right there. So planets that are closer to the star, shorter periods, are hotter. And planets that are out here are colder. The outer solar system planets, Jupiter and Saturn, they're off the edge of the plot. They're too far away. On the vertical axis, I'm showing the size of the planet in relation to the size of Earth. So 1 Earth radius is here, so this is Earth. 4 Earth radii is about the size of Neptune. And 11 Earth radii, oops, wrong button. 11 Earth radii is about the size of Jupiter. So little planets are at the bottom and big planets are at the top. So before 2010, we'd found a bunch of planets. Most of them didn't look anything like the planets in our solar system, and they were a really, really incredible surprise. They were planets the size of Jupiter, gas giants, huge gas giants, that orbited their star in a few days. So Jupiter takes 12 years. Oh, I'm outside the post-it note. I'm sorry for the post-it note. Jupiter takes 12 years to go around our sun. These are planets the size of Jupiter, which have somehow moved all the way over to their star and are orbiting right here. They're thousands of degrees. They're so hot because they're so close to the star that they're literally thousands of degrees. So we call them hot Jupiters because, as Duane said, we're not very imaginative. So this is what we'd found. So it turned out one fellow in 1952, Otto Struve, had actually predicted these planets. He wrote a paper saying, what if you had gas giants planets and they went around their star every 2 or 3 days? Between 1952 and the discovery of these planets in 1995, that paper got 7 citations, mostly people saying, this is ridiculous. Since 1995, that paper's gotten nearly 100 citations, mostly people saying, this guy was a genius. So just goes to show. So this is what we'd found. Why have I picked 2010 as my date? This is the NASA Kepler mission. Can you press play? Thank you, Carly. The NASA Kepler telescope is a 1 meter telescope, so about this big, that was launched in space in 2009. The whole spacecraft is about the size of a small school bus. It's all right if it doesn't play, it's just a GIF of the telescope going around. The goal of the NASA Kepler mission was really interesting, and a question we've had for a really long time. How common are planets like the Earth? When I say planets like the Earth, I mean a rocky planet, so like the planets in our inner solar system, small planets that have a rocky surface, a solid surface that life could exist on. About the right temperature for liquid water, so the surface has to be not too hot, like those hot Jupiters, thousands of degrees, not too cold, like the real Jupiter in our solar system, but just right. And you can already see right there, we've made a really big assumption about life out there in the galaxy. All life on Earth needs liquid water, and we need funding. So we have to start somewhere. So we go to NASA and say, let's look for places where there could be liquid water. All life needs liquid water. There are other solvents out there, other types of chemistry that life could potentially be based on. We just don't really know what that would look like or how to start looking for it. And we want to start somewhere, and we want money. So we say, let's go look for liquid water. The other important thing that Kepler's looking for is planets like the Earth around stars like the Sun. The Sun, as I said, it's a boring yellow G star about halfway through its life. In about 5 billion years, we're in big trouble, but that's a ways away. Most of the stars in the galaxy aren't stars like the Sun. 75% of the stars are small, cool red stars called M-dwarfs. They're much smaller and cooler than the Sun, so their habitable zones, this temperature regime where water could be liquid on the surface, is much closer. You know how Earth takes 365 days? We just established that. If you were to be the right temperature around an M-dwarf, it's more like 2 weeks, maybe a month. So you can be really close to an M-dwarf to be the right temperature. The problem with M-dwarfs is that they put out thousands of times more UV radiation than our sun does. So you know how you put out your SPF 50 before you go outside? SPF 50 million wouldn't help you if you're around an M-dwarf. There's just too much UV radiation. On Earth, we use UV radiation to sterilize clean rooms. This is nasty. So for life on Earth, that would be too much. But maybe there's other kinds of life. But let's stick with what we know. We're looking for planets like the Earth around stars like the Sun. Okay, how does Kepler find planets? It uses the transit method. This is the Sun. Does anyone know what that is? Nobody who saw me give this talk earlier today can answer. Almost. Mercury. It's a little bit smaller than Venus, but Venus is an excellent guess. Every 88 days, Mercury goes around the Sun. If you were an alien civilization, thousands of light years away, lined up just right, and you were just measuring the brightness of the Sun over and over, you wouldn't be able to resolve features like this. It would just be a point of light. If you measured the brightness of that point of light over and over again, we've just heard all about variable stars. If the star's not doing anything, if it's just quiet, then every 88 days you would see a dip. You would see a dip caused by Mercury. Mercury would block 0.002% of the light. So for every million photons that the Sun puts out, Mercury would block 20. That's an incredibly difficult measurement to make. So earlier when I said technology had to catch up with our imaginations, it's because you wouldn't be able to detect that by eye, and even with photographic plates, which is how we started to measure variability 100 years or so ago, you could do better than by eye, but you couldn't do 0.002%. This had to wait for the invention of the CCD, the digital camera that you have all in your smartphones right now. That was invented by astronomers who needed to do better precision measurements of the sky. So you're welcome for selfies. That's on us. So that's a really hard measurement to make, even with CCDs. But luckily, Mercury's not the biggest thing in the solar system. If you were an alien civilization, every 365 days, you would see a little dip caused by the Earth. And Earth would block 0.01% of the light. That's still only 100 photons out of every million. That's a bit rough. But then Jupiter would come along every 12 years and block 1% of the light. Now you start to see why Jupiters were the first planets we found, these hot Jupiters, because they made big enough dips. So you can do this from the ground with a small telescope and a CCD. That's how they were found, the first transiting planets, small telescopes on the ground. Duane and I spent several years using a slightly larger telescope and not finding planets. It's still a really hard measurement to make. There are good things and bad things about the transit method. Once you have the size of the planet from the dip, and you can measure the mass, and there are ways to measure mass, ask me about it later if you're interested, then you have density. Once you have density, you can start to say, is this a rocky planet? Is it an icy planet? Is it a gassy planet? Now we're talking about composition. Now we're starting to get excited. We can also measure the atmospheric properties of these planets if they're transiting, which means we can look for molecules in their atmospheres, water, methane, carbon dioxide. There are problems with the transiting method. As I alluded to, that alien civilization, I don't know why I'm dabbing, but that alien civilization needs to be lined up just right. Most of the alien civilizations in the sky, looking at the sun right now, wouldn't see Earth transit because they're not lined up the right way. So we have to look at hundreds of thousands of stars to find the small number that are transiting. There are also a bunch of things that create dips in the brightness of the star that aren't planets. And frankly, that's what I spend most of my time doing, differentiating between the two. This is a sunspot. It's bigger than Earth, and it creates changes in the brightness of the star. There's all sorts of things that stars do, Duane talked about some of them, that change the brightness and that can hide those dips or create dips that look like planets but aren't. So that's the most frustrating part of my job, and frankly what I spent 4 years as a grad student doing, getting rid of those. Okay, so let's talk about the impact of the Kepler mission. This was pre-2010, Kepler launches, and we found nearly 2,500 planets with Kepler, which has been very exciting. But one important thing, we didn't find a lot of planets like the planets in our solar system. And for a mission that was supposed to find out how common planets like the Earth are, that's a serious bummer. And it turns out that when we were designing the mission, we made a mistake. We thought our sun, our boring middle-aged yellow star, was average, was normal. That the rest of the boring middle-aged yellow stars in the sky would have the same amount of noise, the same number of star spots, the same amount of variability. But we were wrong. When we went out and actually measured it with this telescope, we found out that our sun is quiet. Most stars are actually noisier than our sun. They have more star spots, they have more variability, they have more going on. And that means it's much harder to find planets around them because there's so much happening to the brightness, the dips get obscured. What that means is that we really should have built a bigger telescope. But since we can't change time, we said, if we just observe for longer, if we increase the survey, the Kepler survey from 3.5 years, which was its original length, to 7 years, then we'll recover our original sensitivity and we'll be able to get down here. That was 4 years ago. I'd love to be able to tell you that we got 4 more years of observations and filled this in, but almost immediately, the telescope broke. The spacecraft had a hardware malfunction and we weren't able to keep pointing at the original Kepler field. So this is where we're at. Kepler did not find planets like the Earth, but it did find thousands of incredibly interesting and unexpected planets. So let me tell you about some of them. We found a big diversity. So we found hot Jupiters, which I spoke about. We found hundreds of warm Neptunes. So these are ice giants and ocean worlds that orbit their star between 1 and 100 days. So they're hot. They're much hotter than our Neptune. And they give us this fantastic opportunity to investigate atmospheric properties of if you took Neptune and just heated it up, what would happen? We found lava worlds. So these are planets that are about the size of the Earth, so we think they're rocky, that orbit their stars in less than a day. This is 1 day. So these are planets going around their stars in just hours. So that because they're so close to their stars, their surfaces are thousands of degrees. And what happens to a rock if you heat it up to thousands of degrees? It melts, it turns into lava. So we think that these are literally balls of lava floating around their stars. We also found hundreds of rocky planets. Now, we didn't find rocky planets at the right distance from their stars, but if we extrapolate, if we estimate dangerously what this might look like as you go further out, then we believe that rocky planets are actually incredibly common throughout the galaxy. We think almost every star has rocky planets going around it, which is incredible and something we couldn't say 10 years ago. Since the launch of Kepler, we've been able to find hundreds of rocky planets and estimate that they're everywhere in the galaxy. So that's amazing. One of the biggest mysteries that's come out of Kepler is all the planets that are in here. So in our solar system, you have all of the little rocky planets that go up to the size of Earth, here at 1. Then you have a jump. The next planet is Neptune, up at 4. So then you have Neptune and Uranus and Saturn and Jupiter up here. There's this gap. When we went out there and looked, the most common kind of planet we found was in this size gap. And we don't have any of these planets in our solar system. The reason that's a really interesting mystery is we don't know what they're made of. We don't know whether they are just big rocks, like if you take Earth and scale it up. We don't know whether they're little ice worlds. You take Neptune and you scale it down. We don't know whether there's something we don't have in our solar system, some other mix of materials, maybe just a pure ocean world. And we don't know where they transition from one to the other. What does it look like in here? We don't know. We just have a gap. And there's millions and billions of planets out there in this gap. So this is something that we really want to study more. Okay, I titled the talk On the Road to a Billion Planets. As you heard at the start from Peter, there's 3,777. So we're a ways away. How are we going to get from 3,777 to a billion? This is a tweet for people who don't use Twitter. And this is me asking a year or so ago, is there a Moore's law for exoplanets? Who's heard of Moore's law? It's a law that states that every 2 years or so, computer speed basically doubles. So every 2 years, your processors are twice as fast. And that's called an exponential rise. And I was asking, it looks like the discovery of exoplanets, this is the year, and this is the number of exoplanets that have been found, is rising exponentially. Is there a Moore's law for exoplanets? And one of my colleagues, Eric Mamajek, went and actually did the sensible thing and fit a line to it and said, yeah, exoplanet discoveries are doubling every 27 months. So just over 2 years. So every 2 years, we have almost twice as many planets. And he predicted from that we would hit 1 million planets in 2034 and 1 billion planets in 2057. So how do we get from here to 1 billion planets? I dubbed this Mamajek's law, and I'm trying to make that stick, so just use it in everyday conversation. Whenever you get a chance, throw out Mamajek's law. Okay, so how are we going to find more planets? Kepler looked at an actually quite small patch of the sky. So this is the galaxy, and this is the constellation Cygnus. And this little bunch of squares here, that's the part of the sky that Kepler looked at. It's about the size of your hand. If you go out stargazing after this lecture and put your hand up to the sky, that's the patch of sky that Kepler looked at. Kepler looked at 200,000 stars in this patch of sky, but on average, they're pretty faint and they're pretty far away, which means that all of the exciting things that I talked about that you can do with transiting planets, masses and atmospheres, you can't do with the Kepler planets because the stars are just too far away. But Kepler told us that planets are everywhere and rocky planets are very common. So if we survey all the nearby stars, we should find lots and lots and lots of planets that are much closer than the planets that Kepler found. Enter the TESS mission. So the Transiting Exoplanet Survey Satellite, or TESS, also uses the transit method, just like Kepler. Instead of being a 1 meter telescope like Kepler, it's actually 4 10-centimeter telescopes, little bitty telescopes. If you go out stargazing tonight, you're going to be using bigger telescopes than that outside. But the thing is, Kepler told us that planets are everywhere, so we don't have to look very far to find them. So we can use little telescopes. You know, space is a great advantage, obviously, but little telescopes. And the point is, where Kepler did one patch of the sky, TESS is doing the whole sky. TESS is going to spend 2 years tiling the entire sky in 1 month chunks. It's going to spend the first year doing the southern hemisphere, and then the second year doing the northern hemisphere. I realized earlier today I had to flip my hand motions because I'm in Australia right now. And it's going to do the whole sky. All right, so here's the constellation Cygnus. Thank you so much, Carolyn. That's the Kepler field of view. This is the field of view of one of the 4 TESS cameras. So we're going to zoom out, and you're going to see those 4 cameras get tiled on the sky. So 1, 2, 3, 4. So we're going to do that patch for 28 days. Now we're going to open up the sky, just to show you it a little bit better. This is the original Kepler field. This is what we did with the broken spacecraft. So these are these tiles of the sky. So 27 days at a time, we stare at a patch, then we move a little bit and stare at the next patch. So this is the 2 years. What's interesting is that at the poles, you'll get constant coverage for that whole year. So you'll actually be sensitive to colder, longer period planets at the poles than you are near the equator. So how many planets is TESS going to find? The prediction is that TESS could find up to 16,000 new planets. So we're at 3,777. TESS is going to find a bunch more. And I don't mean planet candidates, I mean real bona fide planets. Most of them will be, this is the, oh, there was one more plot, I'm sorry. It's a histogram, it's okay. This is the size of the planet here in Earth radii again. So 1 is 1 Earth radii. So below Neptune, which is 4, so these 3 bins, there's going to be about 2,000 planets below Neptune. And look at all the ones here in this mystery size range. We're going to be able to measure the masses of these because they're going to be so nearby. We're going to be able to look at the atmospheres of these and finally find out what they actually are and when they start being Earths and when they start being Neptunes. So that's really exciting. I'll just skip that one. Don't worry about movies. All right, so TESS launched in April. Hooray! I got to be there. They asked me to be on TV, which I wasn't super excited about. I got to be a VIP guest, which I was very, very excited about. So there's like a special bus for the VIPs, and I had my badge, and I'm like, excuse me, I'm going to get off my bus now. And then we drove out to the viewing site, and I realized that the public could pay $20 to be at the same viewing site. And I was like, oh, okay, well, yay. This is Dave Latham, who's the science lead of the Kepler, of the TESS mission, and was an important person on Kepler as well. I was very excited to spend the launch with him. He was the one who proposed the mission in 2006. It was 12 years between the first idea, the first germination of a proposal, and the launch, 12 years. This is where the launch viewing site is. So it's a bunch of bleachers on the side of Banana Creek, and then there's a whole bunch of launch pads off in the skyline. The mission is led out of Massachusetts Institute of Technology, MIT, and this was T-1 hour to take a picture. This is a picture of my view. I circled the rocket so that you can see it. When we all sat down in our bleachers, the skyline, as I said, is dotted with launch pads, and they all have these lightning rods around them. And it took us a while to work out which one it was. Eventually, we had to borrow some binoculars and be like, oh, I think that's it. So it's a little more impressive on TV, but it was incredibly exciting to be there because, you know, I was there with hundreds of other people who had worked on this mission for years and years, designing it, building it, pushing NASA to fund it, and getting it to this day. So it was very incredible to be there. This is a movie of the launch. See if you can find the rocket. 5, 4, 3, 2, 1. It's there. The thing is, if you're too close, you die. So they keep you quite far away. Yeah, so the viewing site's about 10 kilometers away from the launch pad. So you definitely get a better view on TV. This was the picture that the person next to me took with their fancy digital camera set up on a tripod with a bigger telephoto lens than we were actually sending into space on the rocket. And all the people that were there were saying, don't take any pictures. Your pictures will be rubbish. Don't take any pictures. Just take in the moment. And then later, get a picture off the internet and say that you took it. So here's a picture I took of the TESS launch. So this was actually taken by an 18-year-old. And of course, the way they take these pictures is they set up the camera on the tripod and then they run away really fast. And then they hide and they press a remote control when the actual thing is launching. So no one's ever actually this close. Everyone's more like my distance away. And I found out, so TESS was launched on a SpaceX Falcon 9. And it was actually the first NASA asset to be launched up on a SpaceX rocket. So we were a little anxious. There had been lots of successful SpaceX launches at that point, which was good, but it was still, you know, a first, which you never like to be the first. But I found out this day that it's called a Falcon 9, not because there was 8 versions before that, but because there are 9 of these Merlin engines. So it's a Falcon with 9 engines. I just thought that was cool. I was there. That's me pointing. Well, I mean, it's an anonymous column of smoke. I could have been anyway, but I was there. And it was very exciting. So this is here to remind me to tell you, the best part, the absolute best part about being on a SpaceX rocket is all the cameras they have everywhere. You can basically watch everything, all of the going up, the detachment, the coming back down. In this case, this little thing here, so when I said Kepler was the size of a school bus, TESS is like the size of a big washing machine. This is TESS. You can actually, if you go to YouTube and look up the TESS deployment, you can see the moment that it detaches. And the thing is, at the actual launch, all of the staff there, all of the people who worked there who'd seen a bajillion rocket launches were just like, get on the bus, come on, I've got to get home, it's dinner time. And we're all just like giddy, like, oh, I've launched, oh my God, like hugging each other and trying to take photos. And the staff are like, please get on the bus. So we're on the bus on the way back to Kennedy Space Center, watching on our phones the thing in space. And we saw it deploy, we saw it detach. And it was just like, amazing, amazing miracle that you could be watching it live. So the video is on YouTube. Go watch it. The moment when TESS detaches from the SpaceX rocket. Very cool. Okay, so it launched in April. Yay. We had our first lights. So that means in NASA mission terms, we turned on all the cameras and they all worked, which is never a given, especially when you put something on a controlled explosion and shoot it into space. Things get jiggled a lot. So they turned on all the cameras and they all worked. There were stars everywhere. It was fantastic. We spent the first 43 days doing this very complicated ballet between the Earth and the Moon to get out to our final orbit. Just last week, just over a week ago, we had our very first 2 weeks of data come down. And the team that I work in is back in America right now analyzing that very first data. All the people I've been with all week are starting to get very annoyed by me because I keep checking my phone every 3 minutes to see if there's any planet candidates yet. Because sometime this week there will be planet candidates, which is very exciting. The first full data release, all of the images and all of the light curves will come out in January. Part of the reason TESS got selected was the promise that all of the data would be made public as quickly as possible so that everybody can help us find planets. As I said, the mission is 2 years, 1 year doing the southern sky, 1 year doing the northern sky, but there's no reason why we have to stop after 2 years, except money. Always comes back to money. The orbit and the spacecraft are actually stable for up to 20 or 30 years. So that really gives us some interesting space to play with. Remember how I said Kepler observed for 3.5 years, nearly 4 years, but we wanted 7. Imagine if TESS observed for 20. Think of the planets we could find then. These are types of planets we haven't been able to search for before because we've never looked at anything for 20 years. So we're super excited about what that might mean. So how do we get to 1 billion planets? So here is this same plot that I showed before. The time is on the bottom. We're in 2018, we're here. And this is the number of planets. So if I put on those 16,000 planets about where we expect them to come out, they end up here. Okay, doesn't look too bad. But now we're only at like 20,000 planets. That's still a ways away. So what's next? All right, can we try and play this one? It's not the start of Star Wars. This is an animation showing the NASA WFIRST mission. So WFIRST is the next big idea we have after James Webb, which is a little bit delayed. WFIRST is an infrared mission which is going to launch hopefully in 2024, and it's going to use a different technique to find planets. So where Kepler and TESS use the transit method, WFIRST is going to monitor the center of the galaxy and look for microlensing events. So microlensing is when a planet and a star go between you and a background star and bend the light from the background star. They act like a magnifying glass. So if you're just monitoring the light of the background star, you see it suddenly get brighter and then suddenly get dimmer again. Not a supernova, has a very specific shape. And depending on the number of stars and planets going by, you can tell from the shape how many there are. So WFIRST is predicted to find something like 100,000 planets by doing a 5-year survey of the galactic bulge. It's going to be, 2024. It's a 2.5 meter telescope, so I can't even get my arms that far apart. It's big. It's designed to find cold planets. So microlensing is sensitive to planets that are much, much further out than the Earth. So Jupiter and Saturn style planets. Using microlensing. And so this is a plot showing the Kepler planets that we found. So this is distance from the star now, basically the same as period. Hot things are over here and cold things are over here. So where Kepler put all of these planets on, WFIRST is expected to put all of these planets on. So it's designed to find the outer solar system things. And it's going to monitor the galactic bulge for 5 years. Let's put on the WFIRST planets. Okay, about 12 years from now. Okay, we're not doing too bad. So for about a decade from now, we can keep Mama Jack's law going. We can keep doubling the number of exoplanets we've known about every 2 years. After that, I don't know, because every other mission is just a twinkle in Paul Hertz's eye at the moment. So that's just as far as we can guess right now. I wanted to finish off by talking about how you could get involved in citizen science. in looking for exoplanets, in helping us to find the next exciting system. Zooniverse is an incredible public platform that hosts data that scientists put up that we've asked for help with. There's an incredible project that, uses cameras in the African desert and their motion sensors, and whenever an animal goes by, it takes a picture, and the picture gets uploaded to Zooniverse, and you say it's a gazelle or a zebra or an elephant, and it helps the scientists keep track of the population and the health of the herds. We chose to put up not pictures of African animals, but planet candidates. So these dips that we found in the light curve, remember, we find tens of thousands of them, and most of them aren't planets. Most of them are caused by other things. So it can be very difficult to explain to a computer the difference between a dip caused by a planet and a dip caused by stellar variability, or a dip caused just by the instrument being noisy. But it's actually pretty easy to show a human how to do it. I can teach you how to do it in 5 minutes. And that's because humans are really good at pattern recognition, also why we're really good at identifying African animals. It was important for us to survive, to be able to do that, to know the dangerous ones. So we loaded up tens of thousands of planet candidates onto a website hosted by Zooniverse called exoplanetexplorers.org. We were lucky enough to be featured on Stargazing Live, which I'm sure some of you have heard of as a big live astronomy event that happened on primetime television, April 2017 and then May 2018. Some of you might have even been involved in the effort this year to break the world record for the number of people stargazing at the same time, which is an incredible achievement. So we were very lucky, obviously, to be featured on this program. And what it meant was that in the 48 hours between the first episode and the last episode of the show, over 10,000 volunteers from the Australian public, of you guys, logged onto the website and made over 2 million classifications, which I estimate saved me about 3 years worth of work, so thank you. And you found, the Australian public found over 180 really new, good-looking candidates. And you found K2-138. I'm going to stop and apologize for the name. You guys didn't get to name it, I'm sorry. Exoplanets are all named after the survey that found them, typically. So K2 is what we started calling the planets we found with the broken part of the Kepler telescope. So Kepler planets get called Kepler, and the broken one gets called K2. So 138 is the 138th system found in the K2 portion of the mission. The reason it's exciting is a very compact system of at least 5 planets. When I say compact, this planet, the innermost planet, has a period of 2.5 days. And the outermost planet here, oh, that's pointing at the wrong one, has a period of 12.8 days. So remember, Mercury, which is the closest planet in our solar system, has a period of 88 days. This is 5 planets inside 13 days. So it's incredibly compact compared to our solar system. And all of the planets are in this mystery size range between 1 and 4 Earth radii. They're all in this strange size range. So it's an incredibly exciting and interesting system. Another thing that's interesting about it is that most of the exoplanet systems we look at are just snapshots in time. We don't know how the planets formed. We don't know where they started. We don't know how they got to where they are today, where we see them. Very few systems, only a handful of systems, tell us exactly how they formed. And this is one of them. You found one of them. The reason we know how the system formed is because the planets have a very special spacing. They're all in a 3:2 resonance. We actually have resonances in our solar system. Neptune and Pluto are in a 3:2 resonance. So for every 3 times Neptune goes around, Pluto goes around twice. The Galilean moons of Jupiter, 3 of them, are in a 4:2:1 resonance. So we do see resonances in our solar system, but this is a chain of 5 resonances in a row. So for every 3 times B goes around, C goes around twice. For every 3 times C goes around, D goes around twice. For every 3 times D goes around, you get it. All the way out, 3:2 resonances. This is the longest chain of these resonances that we found. They're actually all just outside the resonance, which is interesting in itself. The reason this gives us clues to how the planet system formed is because of the special way we see them today. There are competing theories for how planets form and move. In the first theory, the planets form out of a disk of material, clear all of the disk of material away, and then start interacting violently with each other. They smash into each other, they switch places, they fling each other out of the system, they move around. It's very violent. A second way that planets might form and move is that they form in the disk, but before the disk is gone, they start moving and basically getting stuck to the disk. And then they get stuck in resonance. One of them drifts and catches the next one in resonance. Once you're in a resonance, it's like being trapped. It's hard to get out again. So then those two planets, the disk is still there, move and trap a third planet. And then those three planets move and trap a fourth planet. So really the only way we can think of to come up with a sequence of planets that are all trapped in resonance is if they moved very slowly through a disk of material. No violence, no crazy collisions, no interactions, just all smoothly together. So this is one of the few systems that tells us exactly how it formed, and you guys found it. The other interesting thing about this system, and this is just a little aside, it's kind of fun. For the musicians in the audience, a 3:2 resonance is the perfect fifth ratio. So the first two notes of Twinkle Twinkle are a perfect fifth apart. And the frequencies of those two notes have a 3:2 ratio. Now the perfect fifth is an incredibly common interval in Western music. It's found everywhere. I've highlighted some of them here. Oh, maybe I haven't. Some of them are found in here, the ones that are 5 apart. And people have thought for a long time about what the best perfect fifth sounds like. An exact 3:2 ratio of those two frequencies sounds harsh. They beat against each other. It doesn't sound good. So you can get a slightly better sounding perfect fifth by moving just outside the ratio. One of the people who thought about this ratio and what the best perfect fifth was this person. Does anyone recognize him? It's Kepler. The Dutch astronomer that the telescope is named after thought a lot about harmonies. He wrote a book called The Harmonies of the World. And what he was doing was looking at all of the periods in the solar system that they had measured and looking for harmonies, looking for resonances, looking for reasons to match these planets up together. Like, what was the underlying thing that he wrote a lot about planetary laws, and he was trying to work out how they worked. He was looking for resonances. Another thing he really enjoyed was music. And his perfect fifth, he decided that his perfect fifth, which he called the greater imperfect fifth, was the ratio 1.518, which just happens to be the exact ratio of planets C to D in this system. So it's just a coincidence, but I really love this story coming full circle. Kepler was out there looking for this harmonious system of planets, looking for these harmonies, looking for these resonances, and you guys found it. You found his system. You found his harmonious system of 3:2 resonances. So well done, Australian public. All right, if we can play this one, because it's a musical system, because all of the planets are in a 3:2 resonance, it actually sounds really interesting. So if we play a note every time the planet transits, and we have the pitch of the note represent the period, so the shortest period planet has the highest pitch, the longest period planet has the lowest pitch, it makes a song. And it actually sounds good because they're all perfect fifths. This is just your moment of zen. So this is your musical system that you found. Kepler's Harmony of the Worlds. And go to this website for more amazing visualizations and oralizations of exoplanet systems. All right, so summary. It's an incredibly exciting time to be working on exoplanets. We're finding planets that we didn't expect, mystery planets. We're finding planets that someone predicted that we never thought would come true. We're not finding planets we expected to be there. And with TESS, we're expecting to find tens of thousands more planets. They might be new and mysterious. They might be same old, but I'm really excited to find out what we see. One of the really interesting things about this search over the last 20 years, over the last few hundred years, over the last few thousand years, is that every time we find more out about the planets around us in the galaxy, we really learn more about ourselves. So before we went searching, we expected to find systems like our solar system. It was the only system of planets we knew. So all our theories that we'd been developing in order to explain how planets formed and migrated and evolved were designed to reproduce our solar system, to show what we observed. So if you had a theory that created a planetary system that was different from ours, it got thrown away because the planet system we knew was solar system. But now we've gone out there and we've found everything but. All of the systems we found are different. Most of them are different from each other. All of them are different from our solar system. And that's really interesting. It tells us something about ourselves. How different are we? And what implications does that have, for instance, for the search for life? And I wanted to say And I want to leave you by saying, come January, when all the test data from the first 4 months become available, all the images and all the light curves, there will be test citizen science projects on Zooniverse. You should go and find them and look for exoplanets, because the next time I'm giving this talk and talking about an incredible exoplanet system, it could be the one you found. Thank you very much.
Wow, could we have the lights up? That was just fantastic. And what do you think of the skirt? Eh? I must get one. We do have time for a few questions. So if the roving mic.
On the front.
Oh, there we go. That young lady right there, who obviously knows a lot about this stuff.
What would happen if you added or subtracted a planet from our solar system?
Oh, that's a really good question. What would happen if you added or subtracted a planet from our solar system? Now I think our solar system is mature enough that not much would happen. Maybe Jonty can correct me. He's actually the solar system person here. Oh, can fall apart. Okay, don't do that. Let's not. If you were planning on it. Okay, he's the solar system person. Talk to him after. Up the back?
Yeah, I had a couple, but I'll just try to make it one question. I was just curious how they chose where to point Kepler. And it would seem natural to choose somewhere where the stars are closer because maybe you could read them better or brighter, but how did you choose that?
That's a really good question. So remember how I said that transits are an inefficient survey mechanism. You have to look at hundreds of thousands of stars to find the few that are lined up the right way. So knowing the size of the patch of sky we had to balance two things. We had to choose a patch of sky that had the most stars in it possible in order to increase our chances of finding planets, but that wasn't too crowded, because if you have too many stars, like if you look at the center of the galaxy, you can't tell which star has the planet around it. They're all lined up, they're all on top of each other. You have pixels, your CCD has pixels that collect light from the stars. If you have too many stars per pixel, then you can't tell them apart. So we had to have a balance. So we're actually a few degrees out of the galactic plane to get enough stars that we can do good statistics, but not so many that we're crowded. And it's actually really interesting. Even across the Kepler field of view, the crowding changes, and you find many more false positives where the crowding is high, where you have many background stars where you can't tell which one's the planet, than where it's less crowded. Jake's wandering around with it. Thank you, Jake, for running around with Mike.
Yes.
Have you ever observed any sort of accretion disks or any planet formation directly, in a sense, with these exoplanet sort of finding processes?
So not with the transit method. We found planets at the end of their life with the transit method, but there are ways of observing for instance, there's a ALMA, which is the Atacama Large Millimeter Array, which is a huge telescope in Chile. And that's looking at and finding dust rings around forming stars. And you can see structure in the dust rings. You see arcs and clumps, which we believe are planets forming. So there are other ways of doing that, but just not the transit method.
On here? Okay.
You guys are doing a really good job of making Jake run up and down.
While you're getting there, there's one from the young man here.
Can planets disappear? And if they can, how do they disappear?
Can planets disappear? And if they can, how do they disappear? So planets can disappear if you thought they were there and then it turns out they're not there. That's actually happened a few times with Kepler, where we thought we saw a planet, and then when we went back and looked with a better telescope, it wasn't there. A real planet that was always there would have difficulty disappearing. If it got smashed by another planet really hard, which happened a lot of times in our early solar system, then it could turn into smithereens or get kicked out of the solar system. But just vanishing, unlikely.
I have a question, it's a bit weird. About this week mission to the sun and that rocket that's taking it. Now, I've just done a brief calculation, a very rough calculation, because I didn't hear any figures on it, but I estimated that rocket's traveling around 53,000 kilometers an hour. And I was just wondering, when you do find the perfect exoplanet, the one that meets all the requirements that may suggests that there could be life there, or liquid water, as you suggested, then what kind of technology is it going to take to get something to travel out there for further exploration?
Yeah, no, that's a great question. How do we travel to these exoplanets? So the closest exoplanet we found is actually around the closest star that we've found. So Proxima Centauri. So you know Alpha Centauri is the brightest star in the pointers. Alpha Centauri is actually a triple star system, and the closest star to us in that triple star system is Proxima Centauri. And we found a planet around that. That's only 3.8 light years away. So traveling at the speed of light, which is the fastest speed we know, even just having a conversation, the round travel time would be 8 years. And you know, you get annoyed if your friend doesn't text you back the next day. So it's going to be a really long conversation. In terms of technology, we don't have anything yet that will be able to do that in any kind of human lifetime. It would be tens of thousands of years, even at, you know, a small fraction of the speed of light. One of the technologies we've talked about, which is possibly more feasible out of all of the things, is generation ships, where, you know, you build a spaceship that something like a minimum of like 100 people live on, and then they have children, and then they have children, and then they have children, and 50,000 years later, their children get to the planet. That's kind of the only thing that's even remotely feasible right now, given that we can't travel at the speed of light. But we don't actually have that technology. It's just the most feasible thing.
Could I just ask one more question?
Yeah.
One of your graphs showed a prediction of with the TESS mission, how many planets you're going to find and how big they're going to be. Are you predicting that you're going to find less smaller planets because they're harder to find, or you actually think there's more larger planets?
Oh, that's a great question. So the plot showed that TESS will find many more big planets than small planets. We actually, from Kepler, believe that small planets are much more common than big planets, but big planets are much easier to find. So it is the first thing that you said. We just think that TESS will find more bigger planets because they're easier to find.
Okay, sorry, we are going to have to wrap it up now. I'd just like you to join me in thanking Jesse for just an amazing tour. We're very, very privileged to have had our guest speakers here this evening. I think it just goes to show the high esteem that our own astrophysicists are held in by colleagues around the world, that they are prepared to travel all the way here to join in this event. So can you please thank them both. I have a bottle of wine for Jesse. And thank you all so much for coming. I hope you enjoyed this evening. And now we've got some stargazing. What's the instructions for that? You didn't tell me that there was food and nibbles. Oh, that's great. I hope you'll all join us for some food and nibbles. And then about 8:30, those who want to go stargazing, John T will lead the way. So thanks very much. And if you're not going stargazing, travel safely and have a lovely evening.